Oh, it's working. All right. Let's see here. Shares. Introduction. All right. Okay. Sorry for all that. Took a while to get all the thing working. I tried this last semester and I kind of liked it because the students seem to appreciate having the lectures and the discussions recorded and put on Canvas. So that will be available hopefully once this class is over and it uploads it to Zoom and then Canvas eventually. Right. So hi everyone. I'm glad to be back on campus and I hope you are as well. I guess I'll start out just by quickly talking about the topics for today's lecture. Just to summarize that we'll be continuing our discussion on the harmonic waves. I'll give a quick introduction to superposition as it becomes important for some of the discussions we'll have about light interactions with matter. And then we'll talk about 2D and 3D waves, different types of 2D and 3D waves and rays. And then we have time. I wasted quite a bit of time at the beginning, but hopefully we'll have enough time to talk about light interaction with matter as well. And so just to recall, last time we discussed the wave equation in the last lecture, the lecture 2 that should all have hopefully viewed and done the quiz and everything in that. And we showed that this equation, rho squared psi over dou x squared equals 1 over v squared, rho squared psi over dou t squared is the wave equation. It describes elements, functions that, if you like, that propagate, say, to the left or right with some velocity and maintain their shape with time. And so does anyone have questions about lecture 2? I think lecture 1 we mostly spent on like simple discussions and history and so on. Yeah.
So if we take the Fourier transform on both sides, so we'll have we will end up with something with a dispersion relation.
Correct.
But this is the linear relation. So what constraint do we have to put? So but we only take a Fourier transform, but we got a linear. So what for here? So what constraint do we have to put in order to have a linear dispersion?
I mean, it's typical in these situations to assume a linear response for the medium. So that's what you have. But this equation, look, we just derived this assuming that we have some function that's propagating to the right. So it's a very mathematical description. There's not much physics there in it right now. It's a very sort of intuitive description or derivation of the wave equation. For example, I'll give an example. Suppose you take a rope or string, and which is under some tension, and you start shaking it to the left and to the right. Then you can derive what this velocity would be in terms of the tension in the string and various other parameters of the string. But that assumes that, for example, you're only doing small displacements of the string, and the string is not going into some nonlinear regime.
Yeah. Okay? So in a medium, so if we have a linear, we have a linear medium, and then they supply, but the wave also interact with the medium. That will impact the wave propagation in response.
Yeah, it will. Okay, so, and the solution, as I discussed, was psi equal to f of x prime, which is f of x plus or minus vt. Okay. We also introduced the harmonic wave. So the first way to think about that, which we discussed in the last lecture, is that at time t equal to 0, imagine some sinusoidal function that is spread out in space. So as a function of the x coordinate, we imagine that there's some function psi that has this shape, sinusoidal wave, and we showed that the special points in this wave, for example, when the kx equal to 0, then that is a phase equal to 0. When when x equal to lambda over 4, then this kx will take the value pi over 2, where it will then make the sine wave a maximum at plus a, and then at pi it will be 0 again, and then at 3 pi over 2, which is at x equal to 3 lambda over 4, then it will be again at a minimum or negative maximum, if you like, but a minimum is minus a. So there are some important points, like zero phase obviously is important because it means that the phase that the wave has come back to the 0 or its equilibrium position, if you like. And then when it is at a maximum like pi over 2 or 3 pi over 2, that's obviously important. And then when it is back at pi again, then it's going to be again back at 0, and then 2 pi and so on. So the wavelength, as we talked about in the last class, is the number of length units per wave. So that's the spatial period, meaning that's the spacing between, say, this point where it's 0, and also, the phase is basically 0, and this point over here, where again it's 0. Now, of course, the wave is also 0 here, but the difference is it's sort of heading downward, whereas here it's heading upward. So that we're taking into account slightly how things in the neighborhood of that point are also behaving. Okay. So that's the difference between those 2 points. So, but essentially the spacing between, say, any 2 units like this is a lambda. Similarly, say between any 2 maxima, that's probably a little easier to see now, that between any 2 maxima over here is lambda, and so similarly between any 2 minima is also lambda, the wavelength. Okay. And and there's a special name given to the reciprocal of lambda, 1 over lambda, which is often denoted by this simple kappa, and that is called the spatial frequency or the wave number. Okay. And k, which is the parameter over here that appears in front of x, as we've seen, must be equal to 2 pi over lambda, because from this relationship. So for example, now I take the wave as a function of time as well. So when I take a wave, of course, as you increase its, when you put in the time, we know that x has to go to x minus vt for a wave that's propagating to the right. Okay. So I just replace the x at time t equal to 0, this is kx. I replace that x by x minus vt. Okay. And that now, if I now propagate that wave forward by lambda, so if I add lambda or subtract lambda from that coordinate x, any general coordinate in this wave, then writing out this expression, I get a sine kx minus vt plus 2 pi over lambda, which is k, times lambda, so that's 2 pi, so I get plus or minus 2 pi. So again, you see the repetition of the wave, because adding or subtracting 2 pi inside a sinusoidal function makes no difference to the function. So that's why we're able to call k, which is 2 pi over lambda, as the angular spatial frequency or propagation number or angular wave number. Okay, there's just different names. Usually we'll just call it, a lot of times I'll fall into the habit of calling it just k. People just say it's k. Okay. or they might say, oh, it's the spatial frequency. They really mean 2 pi over lambda, which is the angular spatial frequency. But these terms end up being a little bit fudged. People are not very careful about maintaining which one is which. They assume you'll understand from the context of the expression. Okay. Okay, we talked about this in the last class. There was a quiz. Anybody have questions about this part? Yeah.
So does the K does not multiply the VT, or does it multiply the VT?
Out here it does, because K times X minus VT is the expression for the wave. The wave, so initially all I'm saying is, initially imagine there was no time. Time was 0, right? And we think of a wave as just a frozen ripple in space, okay? This wave in space, okay? A harmonic ripple, okay? So it has the same shape of a sinusoidal wave across all of space. In this case, space is just one dimension. So a line or something like that, a string, etc. And then as we allow time to propagate now from starting our clock at time t equal to 0, now we move forward in time, then to the wave as we discussed in the previous lecture, will just be taken by replacing x with x minus vt to represent a wave traveling outward from the origin, for example. Outward meaning to the right in this case. Okay. Yeah.
I think what he means is that there need to be a bracket around that x minus vt on the fourth term of that line equation.
This one?
Yeah.
Mm-hmm.
Around x minus vt.
Oh yeah, you're right. Yes,
Yeah,
I'm sorry.
that's where I was.
You're right. Sorry. Thank you for pointing that out. That's a typo. A sine k x minus vt. So they're bringing the k inside, and this kv is given a special name in time, which is omega. But I will get back to that when we discuss waves and when we come back to say wave propagation in more detail. But so in the end, we can write this as a sine kx minus omega. Okay. And so now if I look at omega, which is equal to now v times k, this is that linear dispersion relation that forget what's your name again? You were asking about linear dispersion.
Yeah, I'm Abraham.
Abraham, yeah. Abraham was asking earlier. So k is of course 2 pi over lambda, e over lambda. And it turns out omega in time can be represented as, I think I mentioned this in the last lecture. If I didn't, sorry, but it's just 2 pi over the time period of the. Okay, this is, I'm sure, familiar to you who have done harmonic oscillators, right? We always call omega as 2 pi over the time period.
Yeah, so,
sorry, let me just finish. Which is equal to 2 pi over t equals 2 pi v over lambda. And so we get v equals lambda over t. Now 1 over t also has a special name, which is the frequency, right? The frequency of the harmonic oscillator or frequency of the wave in hertz, right? So this is lambda times f, the frequency of the wave. Okay. So lambda times f is equal to the velocity of the wave. This is a well-known relationship for all of us. Okay. Which I think I showed in the last lecture. Can't remember. Okay. I should go.
As if in the medium, so when you are doing the linear, when you are doing the linear response, so and then you have to use the time to use a retarded Green's function stuff, and when interacting with a medium, so how does the dispersion and then affect this relation backwards? I was thinking about the linear.
I mean, let's be honest, that's way beyond the syllabus of this class. Okay, so that's something we can discuss outside the class. You know. When we talk about dispersion eventually, I can say a little bit more about it, but it's not going to be a mathematical. It's going to be at a physical, intuitive level. Okay, thanks for pointing that out. All right, so okay, so now I want to talk about the superposition principle, and again, I'll show some equations, but again, we're going to try and think intuitively with physical pictures about superposition as it applies to some of the examples that I'll talk about. So superposition is the idea that if I have two solutions to the wave equation, psi1 and psi2. Now, remember, these are two solutions, which means they exist over all space and time, right? Psi1 might be some f1 x minus vt, and psi2 is some f2 of x minus vt. So at any given point x comma t, then what is the total wave look like is our question. And the answer is that we claim that any combination psi1 plus psi2 is also a solution of the wave equation, which is clear from just this expression, right? Because each of these individually satisfies the expression, the wave equation, therefore the sum of them or the difference or any linear combination will also satisfy the wave equation. Okay. And we usually say that we'll take the simplest of those. Mathematically, any linear combination will be a solution of the wave equation, but physically we say that, for example, with light, that the two electric fields, for example, for light, will just add E1 plus E2, for example, at the point x comma t. Okay, so when two waves arrive at the same place in space, that's the simplest sort of physical picture, and we use that in physics. Okay, then we'll simply add to each other without disrupting or destroying. It's important to think that there could be other possibilities. For example, the presence of psi1 might affect psi2, right? That could be another possibility. That would mean that when psi1 is present, psi2 changes its function based on the presence of psi1. This would be a nonlinear response, for example. Okay, so there are mediums in which that happens, but in our situation, for almost all of light propagation that we are considering in this course, that will not be a factor. The psi1 and psi2 will always add up linearly to each other. Okay, and the resulting disturbance is just the algebraic sum of the disturbances due to the individual waves at that location. So that is illustrated here. So I'll just go over here to this part. Okay, so first we see psi1, which is this gray solid line over here. That is psi1, which is given by the function 1.0 sine kx. Okay, for some k, I'm not going into the detail here. It's some k value, and at time t equal to 0. Now I could try to draw this in x, but it's going to be complicated. So we're just focusing on like this small section of x and seeing what happens as time propagates instead of the other functions. Okay, so at any point x naught, let's say this point over here, psi1 has some value. And what about psi2? Well, psi2 has a value kx plus 1.0 radians. Okay, I'm just adding some phase shift. Well, when you add a phase shift phi, that means x must go backward to have the same sort of value for phase phi, right? Because that's an additional phase, so x must be smaller to have the same value. So at this point, for this x naught to reach the same value in this dashed line, it's back here, right here. At this point here is at the same phase as this point over here. It's displaced to the left compared to the psi1. Is that clear to everyone? Okay. So at this point here, the value of psi2 is higher than the value of psi1, which also is obvious because x plus something over here, kx plus something, so this value is higher at the point x naught. Okay. And so when the two of them add up, you get this third point, which is the sum of psi1 and psi2. Okay. And that is the total wave psi equal to psi1 plus psi2. Now, this was assuming that there's a phase difference of 1.0 radians, okay? So that's for any arc. Essentially, I just chose 1.0 radians, just arbitrary. Let's look at what happens for some special cases. First, we'll assume the phase difference between psi1 and psi2 is 0. Okay, so that is called in phase, because that means that the two waves are exactly in phase with each other, meaning the maxima line up with each other. So the gray line and the dashed line are exactly lining up. The maxima, the minima, the zeros all line up perfectly. And the only reason there's some small difference between them is because the amplitude is 1.0 for psi1 and amplitude is 0.9 for psi2. Okay, so when they are in phase, then the sum of the two waves will of course be almost 2. It will be 1.9 at the maxima and minus 1.9 at the minima. And of course, right here, since it is 0, it'll be 0. Okay, so that is the first thing over here. Now I take some other place over here. Now it's kx minus pi over 3. By the same argument, because of the minus sign for the phase, the wave will advance. The second wave psi2 will be advanced relative to the first wave, the gray line, the gray solid line over here. You can see that psi2 looks like it's gone forward a little bit by that same argument that we just talked about for that. Okay. Again, they start adding up, but now it doesn't quite match up, right? The maxima don't quite match up. Instead, whenever there's a maxima for psi1, this one is slightly lower here. Psi2 is slightly smaller. So that means when the sum of those will definitely not add up all the way to almost 2. That it won't be 1.9 anymore, it'll be something smaller. Similarly, where this one goes through a minimum, the gray line goes through a minimum, well, there's still some value for psi2 over here. The dashed line has some magnitude, therefore the total sum of these two will be having some magnitude. And then eventually, as this approaches, say, a minimum over here, and this one is somewhere over here, you may get a 0 when these two combine together. Okay. So anyway, so it just looks like this wave over here, but now it's smaller in magnitude. Okay, and slightly shifted as well. Okay. We can do this now for 2 pi over 3, same thing. Now you can see the two maxima are almost completely apart from each other. So the dashed line and the dashed line and the gray line, they're almost completely apart from each other. In fact, it's almost like the minimum of the dashed line and the maximum of the gray line are almost coincident with each other. So you can start to see that this wave has gone much closer down in amplitude, and also, of course, it's relatively shifted compared to this initial situation with the in phase amplitude, of the two waves. Here, the phase difference is 2 pi over 3. And then finally, we arrive at phase difference of pi. Okay. And remember, phase difference of pi means that the two waves are apart in spacing by lambda over 2. So that's an important thing I want you to remember always. This should go into your brain at all times, which that when two waves are apart in phase by pi, which means spatially by lambda over 2, now you can see the maxima of this one coincides with the minima of this one. Exactly. Right? And when that happens, these have destructive interference. Okay. So destructive interference means now this resultant wave, the solid black line, is almost 0. And the only reason it's not exactly 0 is, again, these two amplitudes are not exactly the same. 1.0 and 0. And remember, in phase was when the phase difference was what? 0. Or it could be something else too. What else could it be? 2 pi, exactly. 2 pi, 4 pi, all of these will be in phase. Pi, 3 pi, 5 pi, etc. All these will be out of phase, destructive interference. Does that make sense to everyone? So what I just said, that should always remain. No matter I ask you, I wake you up at 3 a.m. in the night and ask you what is out of phase. I want you to remember that. Okay. Pi, phase difference pi, lambda over 2. Should just come out. All right. Okay. So, and of course, we can also calculate. I showed it to you graphically, and a lot of times that's enough for these initial discussions that we're going to be having. But you can do it mathematically, right? You can add up two sinusoids mathematically which are out of phase with each other. In this case, I just show you one example. So 1 times sine x plus 0.9 times sine, and I did the easy case, of course, I'm the professor, so I get to do the easy one, okay, which is sine x minus pi, okay? And so that one is sine x plus, now I use the trigonometric expansion, sine a plus b is sine a cos b, or I'm sorry, it's a minus b, but okay, same thing, sine a cos b minus cos a sine b, okay? That's, so in case you don't remember that or you've lost it from like, a couple years ago, whenever you look at it, please go back and refresh yourself with some trigonometric identities like that, because we will end up using them fairly often in the class. And you can't always rely on having it right in front of you in an exam or test or something. Okay. So, okay. And now here, sine pi is 0, cosine pi is minus 1. Okay, again, these are useful things to remember. Okay. So then sine x minus 0.9 sine x, that gives me 0.1 sine x. Okay. So that if you go back over here, that corresponds to the destructive interference case, which is this one. And again, you can see that makes sense that the two waves are almost are exactly out of phase. So the this 1.0 minus 0.9 is 0.1 times sine kx. Okay, so that is how constructive and destructive interference work between waves. And again, remember the in phase case is constructive. That means phase difference of 0, or the waves have no path difference, as we call it, between the two, because the waves are exactly on top of each other, or they're apart by 2 pi, right? Which is a path difference of lambda. Okay, because if you go back to the origin of wave itself again. Here, path 2 pi corresponds to a path or distance difference of lambda between the two waves. Okay, and phase difference of pi corresponds to a path difference or position difference of lambda over 2. Okay. Okay. Why? All right. So last thing I will leave you with, this is a small assignment for you on Canvas, is to now, instead of the path, so we did the phase difference of pi, but in one of the pictures, I showed you a phase difference of pi over 3. So kx minus pi over 3. So just going back here, we had kx minus pi over 3. So I want you to do this case, the algebraic addition on your own. So meaning, just repeat what I did here with like the pi phase difference, but with pi over 3. And find the value now in terms of a sine x minus theta. Okay, so you'll get some answer, but you have to express it in terms of a sine x minus theta, or kx minus theta. Okay, and report the values of a and theta in Canvas. It's posted on Canvas, so you'll see the assignment there. Okay. All right. Any questions so far about all of it? Right. So now I want to move on to waves in 2 dimensions and 3 dimensions. So we've been talking about one-dimensional waves, meaning just dependence on x, right? So psi is a function of x and t. Okay. Now I want to introduce waves that are a function of x, comma y, and t. Okay. And we'll just generalize right away from the one-dimensional case. We can write down immediately the wave equation as dou squared psi over dou x squared plus dou squared psi over dou y squared equals 1 over v squared dou squared psi over dou t squared. And the solution in the harmonic wave case is sine kx, meaning it can be a wave number or angular spatial frequency of kx, which is k1, just some number kx, and ky. So they can be different, right? Kx and ky can be different in the 2 directions. And of course, again, minus omega t, which is I introduced already as k times v, the velocity. Okay. Yeah.
So sorry, I have a question before that. So when we are adding two waves, so if we have if we add the source, it's a homogeneous term. and then we are shaking the rope, and then that corresponds to, and then can we is a rule we add the wave was the same for that. So the inhomogeneous will bring up extra term derived from Green's function.
No, this is just purely a property of the wave equation. Yeah, it has nothing to do with the solutions. Yeah, the wave equation is linear in psi. So you can always add two solutions of the wave equation together.
Okay. Oh, in that case, we also have a linear operator. But
Yeah,
it's also
the operator is linear. It's a linear differential equation. Yeah. Okay, so if I substitute this solution, a sine kxx plus kyy minus omega t, into this, okay, well, just to do the derivative dou psi over dou x, that will pull out a kx times a sine whatever, and then you do it again, you pull out another kx, so you get kx squared times psi. Similarly with y, you get ky squared times psi. Okay, you're differentiating a sine twice gives you back the sine, but with that coefficient pulled out like that, right? So with square. Same thing on the right hand side, dou squared psi over dou t squared will pull out the omega twice, right? And so you get omega squared, and so that gives you omega squared over v squared times psi. Okay, so for this to be true for all psi, right? We need that omega squared equals v squared times kx squared plus ky squared. Remember, for the 1D case, we had omega equals v times k. Here we have something very similar. Omega equals v times the magnitude square root kx squared plus ky squared, right? So that is like if I created a vector with kx as one component and ky as another component, right? So imagine a vector with the components kx x hat plus ky y hat. So it's a unit. It's a vector that's pointing along this two components kx and ky. I'll do a little sketch in a minute, but the idea is the magnitude of that vector will of course be just square root x squared plus kx squared plus ky squared, right? Everybody knows this, right? So omega, so this expression here, which is omega squared equals v squared times kx squared plus ky squared, can be written as omega equals v times the magnitude of that vector k. Okay, so that's analogous to the 1D case where I said omega equals v times k that I derived on the board for you just a couple minutes ago. But in 2D, now it's not, because there's not just one k, there's two k's, kx and ky. We calculate the square root kx squared plus ky squared as the magnitude of the vector k. So we can represent k as, which I just said here, is kx times x hat plus ky times y hat. And we can write the 2D wave as a sine this vector k dot r, where r is now the vector x times x hat plus y times y hat, right? It's a position vector at any point in space, x comma y. So this is now the form of the 2D wave. Everyone okay with this? Well, that's nice, but what does it mean? What does it look like? What does the solution look like? For a 1D wave, we could sketch it right away because there was x, and we could just write psi of x as just a function which you're all very familiar with, graphing a function as a function of one variable. But now we have two variables. Actually, we have three, right? We have x, y, and t. We have three different variables. And now psi is a function of all three, right? So how do we think about this? Intuitively, visualize it. It's a little tricky, right? We need three dimensions to represent this wave. Even if we freeze time at t equal to 0, we're going to need at least two dimensions. And to represent psi, then we're going to need a third axis, right? Because I think of psi as a function of x comma y. I need the entire xy plane for all the points in my domain, right? In my domain of my function is the entire xy plane. And the actual value of the function psi now would have to be represented along the z direction. So this is already a complicated looking object. So we don't try to deal with it. Okay. We try to simplify it. And the way we do that is we use something called phase fronts or wave fronts. What are they? They are points of constant phase. Okay. We have intuitively also done this when we thought about the sine kx term. We were thinking about the maxima, the minima, and the points of zero amplitude, right? So same idea here. So let's take an example. kx equals k, ky equal to 0. Okay, so this looks almost like our 1D case because the function that we get is a sine kx minus omega t. Okay, but it's not a 1D wave because we have said we are working in 2 dimensions. We have just temporarily set one of the components of k to be 0. Okay. So again, as I said, we need a third axis to represent. So instead, what we do is we draw the domain of the function x and y, right? And anything that looks like kx minus omega t, okay, first of all, ignore t for now, set t equal to 0, this is a sine kx. So means at every point x, okay, there is a line extending along the y-axis, which is a line of constant phase, right? Because if x is constant, x equal to say x naught or x equal to 0, the phase is constant along the entire y-axis because y is not there in the function. Okay. And in fact, usually we draw these phase fronts spaced by lambda. So if this is 0, then this is x equal to lambda. This is x equal to 2 lambda, 3 lambda, 4 lambda. They are all spaced apart by lambda. Sorry, my drawing, I didn't do a good job there. You can clearly see it's not exactly equally spaced. Okay. I was close, but not quite perfect. All right. So these phase fronts, which are all spaced apart by lambda, then represent the points of maximum amplitude, right? Because when x equal to lambda, sine kx is a maximum, right? And so the value of psi is a. Okay, the value of psi is a, and that's also the value where the phase phi is is like 0, 2 pi, 4 pi, etc. Is everyone okay with this representation so far? This is a 2D wave representation. Okay, and we represent it by drawing these phase fronts or wavefronts, as they're called. And so, as I just said, there is a spacing between these wavefronts of lambda. I write it as lambda x because pretty soon we'll generalize to when ky is not 0. Okay, so this is the wavelength along the x direction. Kx lambda x equals 2 pi over kx, and the wave vector k is just kx times x time, which in this case kx is k, so it's just 2 pi over lambda k times x time. Okay, but again you can see this k, this vector is normal to the wavefronts, these planar wavefronts, okay, or line wavefronts in this case.
I think it's better to use the density plot on MATLAB.
I could have done a density plot, but it doesn't give you that much better information because it's actually a little bit confusing to look at as well, right? So because you have to draw everything in the 2D and then represent by a color, basically, what the values. Okay, please go ahead and show it to me. Yeah, I'm happy to display it. I welcome all of you to think about different ways to represent the 2D case. Pretty soon we'll be going to 3D, so that's even more difficult to represent, right? That's where probably a density plot. Anyway, okay. So lines of the constant phase, or wavefronts, or lines of in this case wave lines, or I don't know what you want to call them, phase lines, but generally we just call them phase fronts or wavefronts, and they are lines in this case. Okay. So these are the lines of constant phase, phi equal to phi naught equal to kx naught, plus of course, whenever I do adding 2 pi, it doesn't matter to the phase. So we neglect that each of these is not exactly the same value of the phase, but their phase separated by 2 pi. Okay. And now, of course, we can rotate by 90 degrees. So now the wavefronts or phase fronts are propagating along the y direction. And now the k is along the y-axis and now has the value ky times y hat. It's normal again to the wavefronts. Okay. And the expression is, of course, a sine ky minus omega t. The spacing between the wavefronts is lambda y equals 2 pi over ky. Okay. And every point, so the definition, the full definition of a wavefront or phase front is any point x comma y on the plane in the domain xy of the xy plane such that kxx plus kyy is a constant. Okay. Okay. And we can immediately see from this expression, this kxx plus kyy equal to c, that's the equation of a line in a 2-dimensional space, right? So that is a line, and the line is perpendicular to this vector k, which is kx x hat plus ky y hat. So if we graph the vector kx x hat plus ky y hat, then there's a family of lines, basically all these lines, which are perpendicular to that wavefront, okay, to that vector. And these form the phase front or wavefront, and they are all lines. And they satisfy this equation kxx plus kyy equal to c. Obviously, c changes for each one of these lines. For this line, it might be 0. For that line, it might be c 0 plus 2 pi, etc., etc. Okay? Or minus 2 pi, so on. Okay, so that is the definition of a wavefront or phase front. And we can also do it not just with harmonic waves, but we can also now think about waves that look different than just lines. Okay, for example, if you drop a stone into a pond, then you know that the waves that come out don't look like lines, right? They don't look like lines propagating away from it. Lines might be something like if you were to look down on the ocean and you were to watch the waves coming into the beach, they may sort of look like lines, right? Lines at some angle, if you just graphed all the troughs, they look like lines propagating towards the beach. But if you drop a stone into a pond, now the waves that come out from it look more like the ripples, circular ripples emanating from the source, which is a stone, or a drop of water falling into a pond, a little puddle over here also looks like little ripples emanating outward. Here is a picture of a solar flare on the sun. It causes circular seismic surface ripples. Think about earthquakes, things like that. Well, those are more like faults, so they look more like linear, sort of cylindrical wavefronts, actually. But anyway, so, and in this case, now the phase fronts are no longer lines, they're circles, because they are where the phase is a constant. And now the direction of the k vector is now radial. So at every point here, I would draw the k vector, it would be pointing outward radially from the center, from the origin. Okay? So we start to see that there can be more than just one type of wave, rather not just linear waves, but or plane waves, as I call them, or line waves in 2 dimension, but also circular waves, like in this case. Okay. Okay, now we can generalize to 3 dimensions as well. So extending the 2D argument to 3D, we find the equation of a plane that is normal to the wave vector k and passing through some point. Let's say the point is x0, y0, z0, just some arbitrary point in space. Okay, we don't know what it is. We specify it. For example, it could be the origin, it could be the beginning of your lens system that you're looking at, or some other system that you're looking at, and it's just going to vary depending on the circumstance. So, but here, let's look at this point, x0, y0, z0, and this is the wave psi of RT is a sine k dot r minus omega t. I've just generalized now. I've gone from the 2D case to the 3D case. Okay. So the 2D case we showed is sine k dot r minus omega t. 3D case, I'm saying just extend k to one more dimension and r to one more dimension as well, and that will be now a plane. Okay. So again, as I just said, the line, a wave, a plane can be specified as soon as you tell us what is the normal to the plane and a point that is sitting on the plane. From geometry, we know that as soon as you specify those 2 things, we can specify the equation of the entire plane. How do we do that? Let's take any point xyz that's on the plane. Okay. And now we know that the vector from r minus r0, which is the vector extending from the original point that is given to us, x0, y0, z0, to this arbitrary point xyz. Okay. So I give you some point and tell you it's on the plane, and the plane is normal to the vector k. Okay. Then any point xyz in the plane, the vector from this point, let's call it A, to the point P, where we are trying to find the equation, which is in the plane, then this r minus r0 must be perpendicular to k. So r minus r0 dot product with k must be 0. So now substitute for r and r0. Okay. So if I substitute r as kx xyz, then I'll get r dot k is kxx plus kyy plus kzz. And r0 dot k, I bring it over to the other side, to the right hand side. So that's r0 dot k, which is kx0 plus kx x0 plus ky y0 plus kz z0. That's just a constant because I'm given the value of x0, y0, and z0. I call that constant as a. Okay. So this is the equation of a plane, basically. And where a, as I just said, is kx x0 plus ky y0 plus kz z0. Okay. And k is then k I can also write it as k times alpha, beta, gamma. These are called the direction cosines. I won't get into that. It's fairly easy to take any vector k and resolve it into components along the x, y, z direction. So it has a magnitude k, and then you just project it onto the x, y, and z directions. Those are called the direction cosines alpha, beta, gamma of this k vector. Okay. Okay. And by definition, since k is magnitude k times alpha, beta, gamma, the squares of each of these are the components, must be equal to adding up to 1. Okay. Again, this is not a representation we often use, but you should be aware of it. Okay. All right. So again, the surface that joins all the points of equal phase is called a wavefront, and these wavefronts, these plane waves, will have planar wavefronts. Okay, just a couple more minutes, and I'm done. All right, so plane wavefront propagation. Okay, so as time goes on now, the plane waves will propagate from left to right. So imagine I take one particular plane wave at t equal to 0, and let's say I set it at z equal to 0. Okay, and it's propagating, say, along the z direction. Okay, I can always choose some direction in space, call that the z, or sorry, z, according to the Americans, direction. I grew up in India, so I always tend to say z at the time. So anyway, so t equal to 0, z equal to 0. So now the at some time t equal to t over 8, then z equal to lambda over 8, right? That's the wavefront would have propagated forward by lambda over 8. At time t equal to t over 4, z it will be at the position lambda over 4. 3t over 8, it will be at 3 lambda over 8, etc., until it finally reaches a t equal to the full time period t, and then you'll get back z equal to lambda, basically. And we can also think about what happens in, I'm not going to go into too much detail right now about this, but when two plane waves overlap with each other, we can superpose them, for example. And again, that's just dependent on the angles between the K1 and K2 vectors. So these are two different plane waves, one at K1, which is along the Z direction, and then this one is along the Y and Z direction. So it's tilted with respect to the Z axis. Okay. Okay, here's yet another representation which shows, as time goes on, these wavefronts propagate from left to right, or in general along the K axis, displacement in the direction of the K axis. Okay. So as a final exercise, I have asked you all, I was hoping we would have time to work on it in the class, but we ran out of time because I took so much time to get the technology set up. Hopefully next time we'll go faster. All right, so this is one more exercise for you to submit. So write down the electromagnetic wave, which is the scalar. As I have said already, light is just an electromagnetic wave. Therefore, we can write down the electric field as a wave. And so given all the stuff that we have just discussed, can you write down the propagation of a plane wave along the direction of this unit vector? You can verify for yourself whether this is a unit vector or not. 3i plus 2j, or 3x hat plus 2y hat. I and j are just unit vectors along x and y. Write down the expression for the electric field. Okay, assuming some wavelength, time, amplitude a, and angular frequency omega. Okay, so I will stop here for today, and thanks. See you on Friday.
You change the units from the being taught.
Oh, yeah. Thank you. Sorry, just give me. Let me finish it.
Yeah.